Hello again and welcome to part 5 where we're looking at the Keysight U1282a. So during the last video I was conducting a test where we removed the two fuses from this meter and then I connected a high voltage power supply between each of the current inputs and the common input, and then I attempted to turn that power supply up to 2000 volts and leave it there for a minute. This particular meter has sensors built in that let you know if you have the leads in the right positions. So for example, if we set this current right now, so the way that sensor works is they have to take the voltage, in this case 2000 volts, and drop it down to something that they can actually read. For this particular design, they use a 2.5 meg ohm resistor between this jack and that sensor circuit. So it didn't make any sense that our power supply, which is rated for 40 milliamps a drive, would start the current limit when I had it hooked up to this meter. So I ended up hooking a 2 meg ohm resistor to the output of that power supply, and sure enough the power supply went into current limit. So what's happened is, of course, my test equipment in general doesn't get used just for testing multimeters. About the only thing that does are these transient generators. So because of the hazards involved of using this type of a power supply at such high currents, I had dialed this thing back quite a bit, again just for safety reasons. So what I've done is I've turned this thing back up. So here I have a ohmite resistor. This is a 250k ohm. It's a part number L50J250K. Now this is a 50 watt 5% part. They rate this for 1625 volts, but there's a note in the data sheet, of course, this is actually limited by Ohm's law. So the Vmax is actually a square root of P times R. And of course I'm sure that all of you know Ohm's law, so P is equal to E squared over R. And so we can take P times R is equal to E squared. E is equal to the square root of P times R. So in this case we take the square root of 50 times 250K, and that's equal to 3,535 volts. So this resistor is more than capable of handling the 2000 volts we're about to apply to it. The first thing we'll do is just use our Keysight to measure this. Again, this is a 5% part. You can see about 246k ohms or so. So the way this is set up is we have the output of the power supply. One set of leads goes to our 10x attenuator, which then runs off to this BM869S on the left. And then the other set of leads goes off to our resistor, but I have the BM869 on the right attached in series with that. Let's just turn this off of AC plus DC. So again, with our 10x attenuator, 200 volts times 10 is 2 kV coming out of our power supply, and that 2 kV divided by 250k ohms equals roughly 8 milliamps. So now that we've turned up the current on the power supply, we have to be a little more careful with it, but now it shouldn't have any problem driving the current input of our Keysight meter. You can see I've gone ahead and removed the two fuses again. We'll just leave that cover off, and again we'll place the meter into its microamp mode. These two leads here go back up to our power supply. The second set of leads again go down to our 10x attenuator, which goes off to the BM869 here on the left. Again, we're going to be applying 2000 volts, or again 2 times the maximum rating of the meter. So again, this particular meter is rated for 1000 volts. So we're going to be applying 2000 volts between the common and then the two current inputs. And we'll apply that voltage for 1 minute. Alright, so let's just go ahead and we'll turn up the voltage. And here we have it, so roughly 2000 volts. And let's just wait for a minute and see if anything happens. Okay, there's 1 minute. I'll go ahead and turn off the power supply. We'll move our lead over to the amps input. Again, if you're curious of how much current this is, it's going to be 2000 divided by roughly 2.5 meg. Again, the resistor is going to have a tolerance, and we'd have to subtract off whatever their clamp circuit is. But yeah, somewhere around 800 microamps. Again, if you'd like to prove that, what we can do is we can just place one of our meters in series with it. Alright, let's go ahead and we'll turn on the power supply again. This should be roughly 800 microamps. And you can see it's about 822. And again, we'll just wait for 1 minute to go by. And of course, if we take the 2000 squared divided by our 2.5 mega ohms, that gives us 1.6 watts. Alright, there you have it. We'll turn our power supply back off. So let's just go ahead and we'll reinsert our two fuses. Like so. One thing about this meter, again, because it's watertight, when you go to insert these gaskets, it's a bit of a pain to get these back into the groove. If I lift this back up, you can kind of see right there the grooves that gasket has to fit into. So you have to kind of work it a little bit to get it down in those grooves. Like so. But if you need a meter that's watertight, unfortunately, that's just one of the things that you're going to have to deal with is gaskets. So these two meters are now in series, and then I'll just apply a little bit of current to the input. Alright, and that's pretty much the limit of this power supply. So you can see 1.75 versus 1.75. So it doesn't appear that we've damaged the amp input. Let's just remove our test lead and let's go to microamps. And we'll do the same thing with our little Bryman. And we'll turn up the current again a little bit. Again, this meter takes a little while to respond. You can see both basically reading the same value. We can go up a little bit higher. Looks fine. If you'd like to see microamps, we'll just turn this thing down a little bit. And we'll change this over to the microamp range. Again, you can see both meters reading basically the same value. Let's just try adjusting this down a little bit. Get into a lower range. Of course, my power supply isn't very stable down here, but again, you can see both meters basically reading the same value. So it doesn't look like we've damaged the Keysight meter from this 2 kV test. So I'm sorry about that little bit of confusion. Again, that's just the downside of being a hobbyist. Again, I'm not like some professional meter reviewer. I'm basically just some guy sitting in his home lab playing around with multimeters for the fun of it. So, and of course I use my lab equipment for other experiments. And when you're playing around with high voltages like I do, you tend to want to leave things set to a more safer mode when you put them away. And that's what's happened in this case. So, nothing wrong with the meter. Again, sorry for the confusion. So let's get on with the rest of our testing. Next, we're going to transient test the U1282a. And again, we'll be using the smaller transient generator. And then on my left here, you can see I have our high voltage probe. This will be attached right to the leads of the meter. And this is attached to our oscilloscope. The oscilloscope is currently set for 50 microseconds per division. You can see halfway up we're 2 divisions out, or 100 microsecond. It's set for 500 volts per division. It is currently 2 divisions up, or 1000 volts peak. Again, I use this high voltage probe with the oscilloscope to monitor when the meter starts to break down. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. And again, we'll be flipping the leads to change the polarity. So here we go. This is with the meter obviously attached. You can see that the full width half height changes a little bit. Again, this is because it's now on the ohms mode, so that's going to engage the PTC as well as that high speed clamp. But there's no sign of it breaking down at all. Again, when it breaks down, first of all, we'd hear it. but we'd also see that full width half height reduce quite a bit. You can see the difference with it in voltage mode, how wide the pulse is. Again, that's because the high-speed clamps are not engaged. Alright, that's it. Next we'll functional test the meter and check to see if it's been damaged. And again, that's the purpose of this test box, is to provide us with a quick and convenient way to test the meter. Let's just do a couple of quick checks. Again, this should be roughly 2.5 volts. You can see that's fine. Again, 2.5 volts. Just try it in millivolts, so this will be 115 roughly. And you can see that's fine. So yeah, I'll go through the rest of this off camera. Looks like the U1282a survived the 1000 volt transient just fine. So I've changed our generator. You can see we are now 3 divisions up, or 1,500 volts peak. And again, our full width half height is 2 divisions over, or 100 microseconds. And just like before, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Alright, here we go. Okay, that's it. I'll go ahead and functional test the meter. So our Keysight meter survived that 1,500 volt transient just fine. So here you can see we are 4 divisions up at 500 volts per division, or 2,000 volts peak. Again, halfway up, we're 2 divisions out, or 100 microsecond full width half height. So what I have here is just a small incandescent light bulb. If we look at the resistance of this bulb, so you can see about 29 ohms or so for this one. So what I'm going to do is just go ahead and attach this to our transient generator. And we'll try to get a good shot of this. Alright, so here we go. This will be 5 transients. And again, this is 2,000 volt peak. And you can see the light bulb doesn't even light. Just barely. Let me turn off the lights. Here, I'll put the camera in a little closer. Let's just do another 5 transients. Right there. So even though this light bulb is only rated for 125 volts, I'm currently applying 2,000 volts across it. But again, I only can supply up to about 20 joules. And with that pulse being so small, it's just not enough to light the filament. Alright, so let's go ahead. We'll attach the probes to the meter. And again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. Let's go ahead. And that's our first transient. You can see no sign of a breakdown. Alright, that's it. We'll go ahead and functional test it. Alright, so our Keysight meter survived that transient without any problems. Again, that was 2,000 volts. So I've changed our generator and our scope. So now we are currently set for 1,000 volts per division. You can see we're 2.5 divisions up, or 2,500 volts. Again, it's 50 microseconds per division. If we kind of look over here, again, it's 100 microsecond full width half height. And again, let's just try it with our light bulb. We'll see if we can spot anything going on now without the lights being turned off. Oh yeah, it's a little brighter. Again, we turn off the lights. Again, we're not talking about a lot of energy. Early on when I started this testing, I had people posting how I was hooking these things directly up to some capacitor bank. Of course, you know, if that were true, you're not going to see an exponential decay like this. Again, the way it works is if the meter doesn't break down, all the energy is dissipated inside of this generator in the output network. And that output network is what's controlling the shape of that waveform. So the only time that the meter is going to absorb any energy is if it starts to break down, or in the case of, let's say we have the meter in the resistance mode, it's going to engage that high-speed, low-voltage clamp, and of course then some of it is going to be dissipated across that input resistor as well as the PTC. At these levels now we should start to see the gas discharge tube firing. So let's see if it changes the wave shape at all. Alright, so here we go. Again, this will be 2,500 volts, 100 microsecond full width half height with a 2 ohm source impedance, 5 transients, both positive and negative, with the meter set to each mode. You can see it definitely changes the shape slightly. So that's the result of us kicking that gas discharge tube. Again, not a big deal. Alright, that's it. I'll go ahead and functional test it. Alright, so our meter was not damaged at 2,500 volts. I've reprogrammed our generator. We are now 3 divisions up, or 3,000 volts peak. And again, just for fun, let's get our trusty light bulb out. And let's see if this is any brighter. Alright, you can see it's a little brighter. Again, this will be a 3,000 volt peak transient, 2 ohm source impedance, 100 microsecond full width half height. Again, 5 transients, both positive and negative, with the meter set to each mode. And that was the last transient that was applied to the meter. Again, no signs of anything breaking down. Okay, that's it. I'll go ahead and check out the meter. Again, that was 3,000 volts, and it looks like the meter survived that just fine. So here you can see I've reprogrammed our generator. We're now 4 divisions up, or 4,000 volts peak. Again, let's just have a look with our light bulb. Again, not a lot of energy. You can see quite a bit brighter now. Things are starting to get a little serious. So again, this will be 4,000 volts peak, 100 microsecond full width half height, 2 ohm source impedance, positive and negative transients, 5 each with the meter set to each mode. Again, you can see the decay is a little quicker. Of course, we're activating those gas discharge tubes now. Alright, that's it. Again, that was a 4,000 volt peak transient. I've reprogrammed our generator. I've also had to reset our oscilloscope. So we are now set for 2,000 volts per division. You can see we are 2.5 divisions up, or 5,000 volts peak. Again, I had started these tests running some $50 meters. This particular meter right here, the Amprobe AM510, was the runner-up of that very first test I ran. And this meter was damaged at 5.8 kilovolts. And I used that criteria to set the limits of this generator. So this transient generator can go up to just shy of 6 kilovolts peak. So when I'm talking about meters that are electrically robust, I'm referring to meters that exceed what this Amprobe AM510 did with our original testing. Give you an idea where we're in orange, these are where the meters had failed. And you can see the only meters that exceeded 5,000 volts were this Fluke 101 and this Amprobe AM510. That was it. As we start to look at running with this new transient generator, again, this is our 5,000 volt column right here. And you can see very few meters make it past that. As a matter of fact, our Radio Shack model number 2200087 did, and it looks like the Fluke 107, looks like our whole peak HP760H, and of course we have the Bryman BM869S. We ran 2 of those units. Of course I ran an old Fluke 87V, and that was damaged fairly early on. I had since repaired it, and I tried to repeat the test, and of course that meter did very well that second time through. We never did discover why exactly that very first one failed. Again, I attribute it to maybe some kind of contamination on the meter. But I did purchase a brand new 87V, and you can see that thing still hadn't failed all the way out at the far column. Other meters that passed, it looks like the Fluke 17B Plus. Of course, the Fluke 101. Another meter that did quite well was the Hioki DT4252, the Bryman BM235, the Gaussian Metrowatt M248B, the Bryman 319S, the Bryman BM839, the Bryman BM27S, the Yokogawa TY720, the Bryman BM786, and the Bryman BM789. Both of these meters again did very well. Looks like our UNI-T UT181A that I purchased the second time through failed right at 5 kV. The other one that failed at 5 kV was our Keysight U1282a. Right, so the question now, with the original Keysight meter being damaged at 5,000 volts, I'm real curious to know, is that where this U1282 is going to be damaged at as well? So let's give it a shot. Again, this is going to be a 5,000 volt peak transient, a 100 microsecond full width half height, using a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. And no sign of a breakdown, but again, you can see the full width half height that's shortened up quite a bit. Again, that's because the gas discharge tubes are engaging. Oh, see how the meter is just reset? Of Oh, I just heard it break down. Yep. That's the end of it right there. So at the same transient level where the original Keysight that I tested was damaged at, it's interesting, if we look at the waveform, you see this little spike here right in the center? That's where I believe the meter broke down at. Normally this is a very smooth and clean transient. Well, I think that answers that. Alright, I think what I'd like to do next is just go ahead and take this thing apart. We'll see if we can sort out why it's actually been damaged. Maybe we can repair it. Hard to say. I know that very first Keysight meter I looked at, we damaged that thing well beyond repair. So that one, unfortunately, ended up in the recycle bin. Maybe we can do a little better with this one. It's hard to believe that a company like Keysight can't produce a meter that can survive such a low energy transient. Alright, so let's just see, looking around the meter, yeah, I don't see the tops blowing off anything. So I've gone ahead and removed the circuit board and looked it over, but I'm still not seeing anything obvious. Again, with it making that bit of a crack noise, I'm expecting to see some signs of damage. I've had a good look at this under the microscope and I don't see any physical signs of damage, but as I was kind of going through this I realized I misspoke. I had seen this cable here. Originally I thought this was for the battery connection, but you can see that cable is just for the beeper. The actual battery connections are down here, so those attached to these two springs here. The negative would be on this spring and the positive is on this spring. So the positive spring attaches to this outside ring here, and when the meter is turned on it shorts between these two traces. So you can see right here is the via. That via couples down to this node right here, and then that goes up to some of the diodes and whatnot. Of course this is running on 4 AA's. Normally you're going to see about 6 volts roughly across the battery pack. So what I did is I went ahead and hooked this thing up to my bench power supply. So the way I did that is I just put a sewing needle down inside the via like so. I attached a clip bleed onto here, and then as well as to this spring, which is also attached to the ground point. What's interesting is when I do that, the meter now draws about 180 milliamps. Typically, even with the backlight on, it's going to be lower than that. So I let it sit there and run for a little bit, and then I noticed that these two ICs here are getting very hot. These are an LV595. So I've hit the board with a little bit of Pro Clean to cool it down. And let's go ahead and we'll turn the power supply back on. It's right in this area here. We're building a lot of heat. This control IC is staying cool. Whatever it is, next thing in the chain is on the back side. Let's just flip our board over and let's see what we got here. And it's this device right here, so U17, and that is probably the regulator that's getting so hot. So this is our device right here that's getting hot. It's marked a PLFI, which I believe is a TI-6042 regulator. So I don't believe that this is actually a problem. I could look at it with a scope, but I think what's happening is because something else is loading down this bus, that device is getting hot. So this negative power supply that this produces was used for the RMS to DC converter. That was located in this position here. You can see I've gone ahead and pulled that as well. After removing the RMS to DC converter, I powered up the meter again. It's still drawing a fair amount of current. The DC to DC converter for the negative supply is no longer getting hot, but one of these two transistors is, I believe it's Q6 maybe? I don't know, just looking at it, I think it's this one here. And unfortunately, the main controller IC is now getting warm. I would say if the meter were built by Bryman, I'd probably have a fair chance of actually obtaining the ICs to repair it. But I'd mentioned before that before I'd purchased the very first Keysight meter, I had actually tried to contact Keysight by email and they never responded. That's actually the reason that I purchased the lower end Keysight to run. So I'm very doubtful if I wrote them today using my home email address that they would respond. Probably if I wrote them using my work address they would, but yeah, that's not a place I want to go with this. So I'm going to probably just write this meter off as scrap. Again, we still have to run the life cycle test on the switch, and if this goes anything like the first Keysight meter we looked at, I'm expecting all 4 prongs on the detent spring here to break, and that'll happen probably fairly early on in the testing. What I'm going to do with this meter, assuming that they do break, I'll continue to cycle the meter for the full 50,000 cycles just to see if something else goes wrong with the meter during that, and to get an idea what the wear of the contacts will be. So I'm very disappointed in the meter. Again, this thing cost over $600. Again, this amp probe meter cost less than $50 and was the runner-up in my initial testing. And while I damaged it, you can see right here, Q7H1A replaced. So while it was damaged, I was able to repair this meter. And I've since gone back and transient tested this thing again at 5,000 volts. Handles it no problem. So the fact that you've got a company like Keysight who can't produce a meter at the cost of $600 that'll survive such a low transient, it's pretty discouraging. And it's not just the fact that this particular meter failed. I've ran 2 Keysight meters now, and they were both damaged at that same 5 kV level. If you have any thoughts as far as what to do with this meter besides doing the life cycle testing, feel free to leave it in the comments. I think that's going to be all for this video. Hopefully you enjoyed it. We'll see you in the next video where we begin life cycle testing the switch. Later.